So expanding out these binomials, let's look at how we actually do it. Now what we're actually doing with 1 plus x to the power of n is we're saying 1 plus x times 1 plus x times 1 plus x and so on and so on and so on. N lots of those we're multiplying together. To get an individual term, then what we're basically doing is taking one thing out of each parentheses and multiplying them together. I mean, that's how we expand. So for instance, I could take x out of the first one, then 1 out of the second one, x out of the third one, 1 out of the next one, 1 out of the next one, 1 out of the next one, and then the very last one take out x, and I would end up with x cubed. But that's only one way I could get x cubed. How many different ways could I have ended up with x cubed? Another way I could ask that question is, how many different ways can you choose 3 x's from an n sets of parentheses? Because essentially that's what we're doing. We're saying out of each of these parentheses, I'm going to choose x out of 3 of them. All the rest will be 1. And then when we multiply them together, we'll get x cubed. Well, that goes way back to term 1 now, permutations and combinations. Because our answer is NC3. From n objects, how many ways can I choose 3? So how does that tie in? The general expansion of binomials, and we saw this thing called Pascal's triangle yesterday. We don't actually need the triangle because NCK will always end up being that binomial coefficient, the coefficient of x to the power of k. Because of those n sets of parentheses, we're going to choose x out of k of them. NCK. Now an alternative notation for NCK that we see a fair bit in this binomials is to write it this way. It's not a fraction. Inside these parentheses we have n and then k. It's just an alternative notation that we see. But essentially then we can now say this. The expansion is 1 plus x to the power of n becomes NC0 plus NC1x plus NC2x squared, and so on up to NCnx to the n. So in other words, whatever the power is, that's how many x's we're choosing from the parentheses. That becomes the binomial coefficient. Now of course, just having 1 and x is very limiting. If we make that a plus b to the power of n, we still get those same binomial coefficients, but now we get that pattern of the first term starts to the power of n and goes down by 1, and the second one goes up by 1. The two powers always add together to give n. So I don't actually need to look up Pascal's triangle each time. I can just use what we saw in combinations. So I have to expand out 2 plus 3x to the power of 4, then I know it'll be this. 4c0, 2 to the power of 4, plus 4c1, 2 cubed, 3x to the power of 1, and so on and so on. And I can just put that into a calculator and get my answer. 16 plus 96x, and so on, up to 81x to the power of 4. I said Blaise Pascal discovered all these properties inside the triangle. These are the 3 that probably we use most often. First one is this. NCK will always equal n minus 1 ck minus 1 plus n minus 1 ck. That's basically saying how we create the number. We add the 2 immediately above it. That's what this is saying. We can prove it like this. 1 plus x to the power of n would be 1 plus x times 1 plus x to the power of n minus 1. But 1 plus x to the power of n minus 1 I can now expand out. n minus 1 c0 plus n minus 1 c1x, and so on and so on. Somewhere in the middle there would be these two terms. n minus 1 ck minus 1 x to the power of k minus 1, and n minus 1 ck x to the power of k. So they're in there. If I just look at the coefficients of x to the power of k, it's the only one I'm interested in. Now on the left hand side it would just be nck. Because we said in the expansion of 1 plus x to the power of n, we would have nck x to the power of k. The power matches the nc part. The right hand side I have to do an expansion. Well, 1 would be times the term with the x to the power of k, and x would be times the one with the power of xk minus 1. So its coefficient would be 1 times n minus 1 ck minus 1 plus 1 times n minus 1 ck, which is the right hand side of our identity there. Well, they've got to be the same because I've got to get the same answer. These two things are equal, so therefore we prove that first property. So that's the first property. The second one's a lot simpler. It's basically saying the triangle's symmetrical. So NCK will always be NCN minus K. So in other words, the first one will always be the same as the last one. The second one will always be the same as the second last one. The third one will always be the same as the third last one, and so on and so on. And we could prove that by going back to factorial notation. If you remember, NCK was equal to n factorial on k factorial n minus k factorial. Well, that would be the same as NCN minus k, because I would go, well, that's n factorial on n minus k factorial times k factorial. We get the same thing. So that one's very easy to prove using factorial notation. And the last one, NC0 is equal to NCN is equal to 1. In other words, every row starts and finishes with the number 1. That's all that's saying. Expanding perfect parentheses. This is just a little bit different way of thinking about things. Now we know this. A plus b squared is equal to a squared plus 2ab plus b squared. But I think about it this way. A plus b squared. I'm going to have a plus b times a plus b, and I'm going to grab one term out of each of them. So I should always end up with something that has two pronumerals. Now they might be the same, they might be different. So I could start this way. I said, well, what are all the different ways of writing two pronumerals, and I'm only going to use the letters a and b? How could I do it? I could write a squared, because that would be a times a, there's two pronumerals. I could write b squared, that's b times b. Or I could write a times b, but that's pretty much the only pattern that I could have. So the question now is, well, how many ways could I arrange two a's or two b's? Well, there's only one way of doing that, AA. How many ways could I arrange one A and one B? Well, there's two ways of doing that, or using permutations, 2 factorial. And you see we get the same thing. Written slightly different, so I've got one lot of a squared plus b squared plus two lots of ab. Well, that is indeed a plus b all squared. But using that idea, it doesn't actually matter. I don't have to have a binomial, because I can use that same idea. A plus b plus c plus all the way up to whatever letter I like, I've just stopped at n, all the different ways I could do it. Well, again, I could have a squared, I could have b squared, I could have c squared, all the way up to, I could have n squared, but there'd only be one way of doing that, a times a, that idea. Or I could have a times b, or a times c, or a times n, or b times c, or all of those different ones. Well, there'd be two ways, or 2 factorial ways of arranging those two letters. So I could expand that whole thing out. Let's push that idea through to a cubic. So a plus b all cubed. What are all the different ways of writing 3 pronumerals? But again, I'm only going to use the letters a and b. I could have a times a, so I only use one of the pronumerals but use it 3 times. I could use one pronumeral once and the other pronumeral twice. So a times b squared, or a squared times b, and that's pretty much it. That covers it all. So then the question is, well, how many ways could I arrange these things? So how many ways could I arrange 3 A's or 3 B's? There's only one way, a times a times a. How many ways could I arrange 2 A's and 1 B? Or I could ask the same question of 2 B's and 1 A, it doesn't really matter. 2 objects are the same and one's different. Well, we saw that in those word type questions. We said, well, it's 3 factorial, because there's 3 objects, but dividing by the repetitions. So the A's occurring twice, so we get 2 factorial. Well, 3 factorial on 2 factorial, that's 3. If you think of your expansion for a plus b all cubed, that's what it is. Written slightly different. Normally we'd see it as a cubed plus 3a squared b plus 3ab squared plus b cubed. So now I could expand out a plus b plus c all cubed. All the different ways of writing, but now I'm using an a, b and a c as well. So I could have used one of them 3 times, a cubed plus b cubed plus c cubed. I could use one of them twice and the other one once. So a squared b, a squared c, ab squared, ac squared, b squared c, bc squared. Or I could just pick one of each of them, a, b and c. How many ways can we arrange? Well, given the a cubed, 1. a times a times a. How many ways could I arrange 2 a's and a b? Well, 3 factorial on 2 factorial. But now my next question. How many ways could I arrange the letters a, b and c? Well, that would be 3 factorial. 3 objects, arranging them. So there is my expansion for a plus b plus c all cubed. What about para 4 then? What are all the ways I could arrange 4 a's or 4 b's, there'd be one way. What about if I had 1a and 3 b's? So a, b, b, b. Well, that'd be 4 factorial on 3 factorial for the repetitions. The other possibility I could have would be a squared, b squared. Get 2 of both of them. Well, that'd be 4 factorial on 2 factorial, 2 factorial. There's my expansion for a plus b to the power of 4. Let's go crazy. A plus b plus c to the power of 4. I could have a to the power of 4 plus b to the power of 4 plus c to the power of 4. Certainly could have that. But what about if I grabbed 1 of one pronumeral and 3 of the others, but now there's all these different possibilities. I could have ab cubed, ac cubed, a cubed b, bc cubed, a cubed c, b cubed c, but the question again is how many ways could I arrange 1a and 3 b's, 4 factorial and 3 factorial? How else could I get 4 objects? I could have 1a, 1b and 2 c's, for instance. Or it might be 1a, 2 b's and a c, or it might be 2 a's, 1 b and a c. How many ways could I arrange a, b, c, c? 4 factorial and 2 factorial. What else could I have? Well, I could have 2 of each of them. So maybe a squared, b squared, a squared, c squared, b squared, c squared. 4 factorial and 2 factorial, 2 factorial. There's the expansion for a plus b plus c all to the power of 4. Now, at this point I should probably say, don't panic, you're never going to be asked to do that. What I'm showing you here is how we can actually use our ideas from permutations and combinations in expansion of binomials. 15b, as I say, trust me, it will not go to that extent. That expanding the perfect parentheses is maybe me going a little bit crazy there, but just to show you how we can use these ideas in more than one area.